Okay, so welcome back. Today we're going to simplify what can be a fairly confusing concept in mathematics, and that is called trigonometry. And as you see here, we're going to use some visual pictures to help you understand things in a very simple manner. So now one of the goals and challenges in math and science and engineering is putting numbers to stuff and figuring out how you can define things with numbers. So what do I mean by that? Well, we humans tend to speak of things and describe things in fairly vague generalizations that are more emotional than they are factual and numeric. So for example, we got a guy here, let's say he was talking to his friend on the phone, and he said, "Hey, it's really hot outside." Is that really useful information? Well, it conveys that it might be warm to him, but if you normally live in Africa in the desert, or you live in Alaska in the cold, it may have very different meanings. So it's kind of a vague generalization that may not mean much to the people that you're trying to talk to. The same thing, they may say, well, that car's going fast, or that box is big. There's a lot of vague generalizations that you can't really use to analyze things and understand exactly how they are and how they work. So again, one of the big challenges and goals in math, science, and engineering is figuring out a way to put numbers to things to actually define exactly what their properties are so that you can analyze it and you can understand in the real world what's going on without having to rely on vague generalizations. So let's take an example here. Let's say we got this guy talking to his buddy on the phone, and he says to his buddy, "Hey, there's a box near me." The buddy will say, "Yeah, okay, there's a box near you." Well, first of all, where is it? What do you mean near you? Where is it relative to you? And he'll respond, "Well, it's over there." And the buddy says, "Well, wait a minute, what's over there? I don't know, I'm not there." So now this guy has the challenge of trying to figure out some way to convey to his buddy a description of its location that makes sense to his buddy. So now he's got the challenge. How can I describe to my buddy where that box is so that it means something? So what's he going to do? What's he going to tell his buddy? Well, there's many different ways he can choose to describe the location of the box. Let's first take a look at how he can describe the location relative to where he's standing. Well, if he's got a tape measure, what he can do is he can take out the tape measure and he can measure the distance between himself and the box. And he may measure that distance and say, okay, it's 10.5 feet from where I'm standing. So he tells his buddy, okay, that box is 10.5 feet away. Is he done? Well, kind of. He says it's 10.5 feet away, but the buddy says, well, wait a minute, is it in front of you or is it back of you? Is it on your right-hand side, your left-hand side? Where is it relative to you? So now how is he going to define the location of the box other than that it's 10.5 feet away? Well, somehow he has to come up with a way to define whether it's in front of him or to the right, to the left, or behind. Well, how is he going to do that? Well, one option is to make some what are called axis lines that are fixed lines that he can describe the location relative to those lines. So for example, this line goes to his right, this line goes to the left, and then this line goes front and behind him. So now he can say, okay, well, it's between this axis line that's on my right and the axis line in front of me. So he's now removing the possibility that's behind him or on his left, but still he doesn't have a real clear indication. So how is he going to figure out where this box is relative to these lines? Well, one way he can do it is he can make up a definition that says, okay, I'm going to define a kind of a rotation that goes from this line all the way around and comes back to this line. And I'm going to define the amount of rotation as a Fizzbigler. He's going to make up the term Fizzbigler. He's going to say, okay, randomly, I've decided I'm going to call it Fizzbiglers, and the entire rotation around this circle back to this axis is 4 Fizzbiglers. So that means that in front of me is 1 Fizzbigler, to my left is 2 Fizzbiglers, behind me is 3 Fizzbiglers, and coming back to the right-hand side is 4 Fizzbiglers. So an entire rotation is 4 Fizzbiglers. So now, using that arbitrary definition, he can say, well, it's not 1 Fizzbigler in front of me, and it's not 0 Fizzbiglers to the right of me. It's like half of that, because it's only half of 1 Fizzbigler rotation. So if the entire rotation is 4, this is like half. So he tells his buddy, okay, it's like half a Fizzbigler. And the buddy will say, what the heck are you talking about? Well, it's a half a Fizzbigler. So if the buddy's smart, he'll say, okay, what's a full rotation? And then he might say, well, it's 4 Fizzbiglers, and this is half. So then the buddy, if he's smart, will say, oh, okay, so it's half out of 4. So it's probably in between his front and his right-hand side, and it's 10.5 feet away. Okay, so I got a pretty good idea. Or the buddy might say, well, dude, in the real world, we deal with things called degrees and also things called radians. And those they're like Fizzbiglers, but they're a little bit different. They define rotation, but with degrees, a full rotation, instead of 4 Fizzbiglers, it's 360 degrees. And in the world of radians, a full rotation is like 6.28 something radians. So we got 4 Fizzbiglers for full rotation. We got 360 degrees for a full rotation. We got 6.28 radians for a full rotation. So no matter what arbitrary units you use for rotation, as long as you understand what all that means, that it's based on this 0 right-hand axis, and you know what a full rotation is, then you're pretty well set. You can define the location of any object here on the distance it is from this, what's called an origin, as long as you know what the origin is, and how many degrees or radians or Fizzbiglers from this axis. If everybody is working with the same terminology, you can define any object on this plane here based on the distance and the rotation. So pretty cool. Now you've got a way to define the location of any object on this plane in terms of distance and rotation. Now, what if you don't have a way to measure that rotation? You don't know how to measure a Fizzbigler or a degree or a radian. You do have this tape measure you use to measure the distance, so maybe you can find some way to measure the location with a tape measure. Well, if you make a more detailed grid here, maybe you can use the tape measure. Instead of just measuring a direct distance, you can measure on this x-axis a distance and on the y-axis a distance to this object. And isn't that exactly the same using different values? Instead of a distance and a rotation, it's a distance on the x and a distance on the y. So now we have 2 ways to measure an object's location on this plane. One is a distance and a rotation. The other is an x-axis distance and a y-axis distance. Well, now at this point, trigonometry looks pretty straightforward, right? We've got this little blue sphere and we're finding a couple ways to define its location, either a distance and an angle or an x and y coordinate. Well, one of the challenges in trigonometry becomes that you often, very often, have to convert between these 2 methods of locating an object. So let's figure out how we might go about converting between location values of a magnitude and angle or an x and y location. Well, one thing we can do is we can say, hey, let's take our arrow here and leave the magnitude unchanged and just rotate it, change its angle, and see how these x and y values respond. And maybe from that we can figure out what's a mathematical relation we can use to define any x and y value based on our angle. So what I'm going to do is I'm going to vary this arrow, and you can see how the x and y values change as we vary the angle. You can see here the y-axis value is increasing and now it's decreasing, and you can see the x-axis value is doing something similar but a little bit different. So let's start by focusing only on this y-axis value and see how it changes as we vary the angle. And what I've got here is a moving chart showing the result of this y-axis value over time as we vary the angle of this arrow. And you can see it's now going to 0, and it's going here, it's going negative, and now it's going back to 0 and going positive to a peak, and then coming back down to 0 and going to a negative maximum, and so on. And what you see here, this waveform describes the y-axis value as you vary the angle. And you may be familiar with this waveform. It is what has been called over many years a sine wave. And that's kind of an arbitrary name that was given to it many, many decades ago. And this sine wave is something you will see everywhere in the engineering, science, physics world. It's a very, very common phenomenon. It's a physical phenomenon. So basically what this is saying is for any angle, I can define the y-axis value by looking at this sine wave. So we can use this sine wave as a way to convert between the angle and the y-axis value. The same thing applies for the x-axis value, but it's a little bit different. So let's take a look at that. So now I've added the x-axis value in orange here, and you can see it is also a sine wave, but it's a little bit different. It's offset. And you can see as this rotates, the y-axis value here is a maximum positive, while the x-axis is 0. And you can see they're kind of a little bit different. But they are both defined by this sine wave. The difference is the timing of the maximum and minimum values. The orange value is what's called a cosine. Again, it's a sine wave, but a little bit different. As you change the angle, these things vary a little bit different, but they're always in a sine wave relationship. So now what we've determined is that if we want to convert between this magnitude and angle of this arrow and the x and y values, we're going to have to use the sine wave to tell us what the relationship is. So now one of the challenges with a sine wave is that it is a very, very, very common physical phenomenon, but there's no very simple algorithm you can use to define it. And what happens is people generally will take this sine wave and use what's called a lookup table to define the values of the sine waves. Now, thankfully, in most programming languages and areas where you need to calculate sine wave values, they already have built-in functions that will do that for you. But under the hood, sometimes what they're doing is, like I say, they're using a lookup table where they've previously pre-calculated the sine wave values using some fairly complex calculations. And basically, you've got like a spreadsheet here where you say, okay, I want the sine wave value of 110 degrees, and you just use this lookup table. It looks it up, and it gives you a value. So sine waves, very, very important. And in the future, we'll talk a little bit more about how amazing they are and how they're used everywhere else. So now that we have a basic concept about sine waves and cosine waves, what we're going to do in future videos in this playlist is we're going to get into a little bit more depth about trigonometry and how to do other conversions. So if you like any of these videos, I encourage you to hit the like button, subscribe, hit the bell notifications, but most of all, please let others know that we're here so we get some views. Really appreciate it. Otherwise, take care. Have a really good day. Thanks.